So thank you, Mircea, for the introduction, for inviting me, and thank you, Kadina and Mircea, for putting together this event. So it's quite unfortunate I cannot be there. Daniela couldn't come for the reason of catching COVID, and I couldn't come for the reason of not having a visa. So then when I realized this, I started thinking about the relative benefits of each of these two conditions, the condition of having COVID and the condition of needing a visa to come to the UK. And then I thought that they are both effectively diseases, because the condition of needing a visa to come to the UK is a hereditary condition. So, anyway, so you should all interrupt me and shout out, questions and stuff. So I realize this is late and everybody is tired, so this is going to be a very relaxed talk. And also gentle sort of come back to the mini course, to the green mini course, and some lectures and hopefully problem sessions that go with it. So let's recall this moment from Doug's talk from yesterday. So he described how we can calculate asymptotics when n goes to infinity for minima of recent interactions, right? So we are thinking about recent interactions when the interaction is short range, meaning that the exponent is bigger than the dimension of the ambient space. And so turns out that we can calculate the asymptotics when n goes to infinity. Life is good. Then we have some other arguments that will take care of extending these asymptotics to some fairly general sets, right? So instead of maybe putting points inside a cube, you can put them on some quite rough sets and still be able to calculate asymptotics of minimal energy. And so the question that I want us to think about for the next 20 minutes is how far does this type of reasoning go, right? Specifically this extension argument, right? So from now on, let's say we have a way to calculate asymptotics on cubes. How far do we go? From cubes to very non-smooth sets, right? And to answer that, along the way, let's think about other functionals. So this is a sort of a functional, right? It takes omega n and it sends it to a number, right? So maybe omega n to r plus or something like that. So let's think about other situations where the input is a configuration denoted as usual omega n endpoint configuration in RD. So maybe let me write this right here. This is in RD, right? And then we have all kinds of functionals that send this configuration to a number. And there are some quite classical functions of this form, such as, for instance, the optimal covering radius, right? So given a set, this gray set here, you're trying to find the position of red particles such that any point of the gray set is reachable is reachable by the shortest distance from one of the red particles, right? So this is the problem of optimal covering. This is a quite old question, which basically has to do with metric entropy, right? So this is basically calculating metric entropy of this gray set, which you can think of as the amount of information that the set contains, right? So if you can transmit the positions of red particles, then you can think of this covering as a way to encode the gray set via the red particles. So that's one such problem, right? So I'll have three more in addition to this one. Another one that Ed may perhaps talk about sometime soon is the optimal polarization, which is good to think of on an intuitive level as the question of lighting up a dark set, right? So you have a dark set like that. So this is a dark room, and you're allowed to place lights in it. And these lights, they have this rather odd property that the propagation of illumination is governed by this inverse power law, right? So this is the optimal polarization with the Riesz kernel. And generally speaking, I will be interested in S bigger than D, but okay, you can also ask the same question for other exponents, right? And the goal is to maximize the illumination of the darkest point in your set, right? So one lamp produces result somewhat similar to this, and you're allowed to place n lamps into your set and illuminate it as best as you can, and then send the number of lamps to infinity, because that's what is practical, obviously. Okay, so some more examples to the same effect, right? So remember, input is a configuration, output is a number. So okay, I'm not sure why I suddenly have asterisks. That's a typo. So the input is a configuration. The output is the sum of k nearest interactions. So each point fills a fixed number of its nearest neighbors. Okay, it's already shown on there. You can see. So in this case, 5 nearest neighbors, and then you add up sums like this, where maybe there is a weight that depends on the position of the center that you're looking at, and you're adding up these inverse power interactions. And here, okay, here, not necessarily S bigger than D, just S, let's say, bigger than 0. So this is something, this is an interaction that we'll come back to. Another very classical, very nice classical functional is optimal quantization error. This is somewhat similar to that metric entropy question, right? So metric entropy goes back to Kolmogorov. So Kolmogorov read Shannon's paper on information, and then he decided to do something similar for geometry. Well, this object now goes straight back to Shannon. The right way to think about it is you're again transmitting your set, your continuous set or continuous measure mu. Right, so you have some maybe continuous with respect to Lebesgue, let's say, measure mu, and you're transmitting it via these discrete positions, right? And the goal is to minimize second moments of the Voronoi cells around your centers, around these discrete signals. So this is basically discretization, the problem of discretization or quantization of a continuous signal. And minimization of the expected error. So basically minimizing variance of these Voronoi cells. Okay, yet another way to think about it, if you like optimal transport, yet another way to think about this problem is I give you a continuous measure mu, right? Your goal is to produce a discrete probability measure supported on n points that is the closest to this continuous measure mu in Wasserstein W2 distance. Right? That's an equivalent formulation. Okay, so you have 4 different situations, 4 different problems where given a collection of points, your functional produces some sort of number. And so we would like to study these functionals. Turns out we can have a general asymptotic theory for all of them that is shared among all of them. So just to give you a sense of what such an asymptotic theory would look like, let's focus on these guys. So again, we're summing up for each point, we're summing up, let's say 5 or 20 or any fixed number of k nearest neighbors with inverse powers like this. We might put in weight, but if you don't like it, don't think about it. We might put in external field, but again, if you don't like it, you don't have to think about it either. Right, so this is the setup. Now what do? Well, we minimize this energy. So we send it to minimum, and we look at the minimal value, and we look at the configuration where it is attained. So if W and V are lower semi-continuous, and you're minimizing on a compact set, then this makes sense. So just like any of these other interactions that you discussed, this one produces nice local structures, right? So if you zoom in, again, you see all these scars and whatnot. So even though this is a very, very local interaction, it still tries to look as flat as possible. So it has quite rigid, hence the rigidity. So we wanted rigidity for the purposes of workshop title. Here it is. This in 2D, this is rigidly hexagonal, right? And then, okay, if you're wondering what this picture is, this is not really an appropriate picture because I think the density here is proportional to Gaussian curvature. I really should have redone this picture, but my MATLAB license expired. So we have to look at this one. But anyway, so
and a new boss.
Yeah, so anyway, this is some sort of picture that shows you hexagons and scars at that. Okay, so in case you didn't notice or didn't realize, everything that's green is hexagonal, everything that's not green is either a pentagon or a heptagon. Right, so exactly as you would expect, you have these elastic looking energy, which is somehow implicitly built into these interactions. Okay.
Can I ask, so by short range, you mean S very large?
No. This, okay. Once you do your 5 nearest neighbors, you can forget about restrictions on S. Right. So you asked whether S has to be very large, right?
Because then it gets more like a hard sphere repulsion.
Yeah, exactly. Yeah, this is like a hard sphere question with scale invariance. Yep, precisely. Yeah, which is kind of like the goal, right? So the covering before and the hard sphere question, great. All of these very nice. They fit exactly the kind of situation that we want. Short range interactions, all of them. Yeah. So for this interaction and for all of the other ones, here are the typical statements that you can derive, right, using these sort of shared tools. So that you can study the asymptotics of minimal values. Now, okay, maybe I should tell you a little bit about what is written here. Not in too much detail, obviously. Let's see. So this is a variational functional, right? You will ask, but what is rho? Okay, I wrote rho down here for you. So this is not particularly enlightening, but I can make it more enlightening by saying that this is an expression which minimizes this functional over rows. So you just constrain rows to make them probability densities, right? So this is your rows, and then this is maybe a row star or something that minimizes an integral like this with some slightly implicit constant that minimizes the integral like this over such probability densities. So this is a nice exercise in calculus of variations. Write the integral, take cross variation, and so on. So exercise. Okay, so now where am I going with this, right? So you can study asymptotics, you can study limiting distribution. Why did I list all this zoo of different interactions? Like somebody in the audience suggested, also the hard sphere problem, like packing hard spheres is another example of something that looks very similar. Great. So what is going on here, right? So what are the properties that these functionals have that enable us to compute these asymptotics? And basically, you want functional from the space of configurations. So it takes configurations and it takes sets, right? So maybe, okay, I'll write a pair. Okay, it's actually written over there. So this is the input to your functional, configuration and a set, right? You have to be monotonic in the set. So bigger sets, for instance, lead to bigger covering radii and so on. Smaller sets, smaller covering radii, things like that. The interaction has to be local, right? This is true both for hard spheres and for all of the aforementioned interactions. If you're careful or super quick, you may say, but something is fishy here. It's not always some, right? So when, for instance, you're talking about covering, and you have two sets, right? And you want they are far apart, and you want to cover both of them. The worst covering is the maximum of coverings on these two sets, right? And that's what you want to minimize. If you're packing into two sets, if you're packing hard spheres and you're allowed to inflate them and so on, then it's the let's see. So it's the, well, I guess then you have to look at the minimal bulk. Anyway, the point being here is this is not really a plus. This is a homogeneous degree 1 function, which is convex in the correct direction, and so on. So this is a homogeneous degree 1 function. The point being that if you have pieces of a set, then asymptotics on the union is uniquely identified through asymptotics on pieces.
So Alex,
right? And,
Alex,
yeah.
So the A is in the denominator is the union.
Yes. Okay. Sure. Yeah. Yeah. Thanks. Yeah. Yes, indeed. So this is. Let me draw the picture for you. This is A1. This is A2, and A is the union. In this case, it's disjoint. And finally, and this is a bit subtle. So if you look back, to this work of Kolmogorov and so on, they didn't think about stability under perturbations or continuity under perturbations. So if you want to know the details, what kind of perturbations and so on, basically perturbations of small measure, right? So you look at symmetric difference of sets and measure of that and so on. That's the kind of perturbation you're interested in. And they didn't have this property, and they were unable to push to some quite rough sets that you can take care of using this property. Okay, so what functionals have these properties? Everything are listed, and then some. So okay, for purposes of time, I think I have 5 minutes left. Is that right, Mircea? I forgot when we started. I think we started. We started
in 5 and 10 minutes.
Okay, 5 minutes. Great. So just for the purposes of introducing something new, there are graph theoretic functionals that have this property where different parts of graph do not interact in some sense. So the asymptotics on the union of two pieces of graph is uniquely determined by asymptotics on subparts of graph. Right? So it doesn't have to be in quite the Euclidean metric space. It can be other metric spaces as well. So I already mentioned optimal covering and so on. So using this approach, you can push the asymptotics to sets that are not necessarily Jordan measurable. And so we looked around and okay, so people cared up to some point, people only cared about Jordan measurable sets. So for instance, there is a book by Graf D on optimal quantization, and they ask, okay, does this asymptotic work for general compact subsets of RD, for instance? Right, and well, this sort of answers that question. This approach with the removing stability, and way before that, something like in 60s or 50s, Kolmogorov also proves these asymptotics of optimal covering, and he doesn't care about non-Jordan measurable sets either. So basically, as far as we could tell, this is the first extension. And in case you're wondering, right, you may say, but surely the optimal quantizers people did something like this. Well, we couldn't find that either. So we checked Gruber, and he also only takes care of Jordan measurable sets. So, okay, this is just some literature. In case you don't know what the literature, you're probably not interested. So that's fine too. Right? Okay. So some other interactions. So territorial animals, they only care about their nearest neighbor, right? So if you have a squirrel in your backyard, that squirrel only knows about the squirrel in your neighbor's backyard, and so on and so forth. So both of these figures are taken from this nice overview paper on optimal quantizers, so which are another example of this short range interaction, as you have seen. All right. So what's this theorem? So there was, of course, there's generalization of what I told you about k nearest neighbor Rees, or the theorems about optimal quantizers. You can write a single theorem which covers both. Here, I'm not trying to do that, but basically you have to introduce some signs, to take care of whether you're minimizing or maximizing and so on, and little technical things like that. But it all works out really nicely. So some interesting things that follow out from this theorem is basically that the scaling rate, which for Rees, this was n to 1 plus s over d, in case you're trying to make sense of this terrible, very crowded slide, right? So this is the scaling rate for Rees interactions, for instance, for the short range Rees, either truncated or s bigger than d, however you like it. So it turns out that there is sort of a lot of rigidity again in the rate function. So as soon as you know that you scale in a certain fashion, you know that the scaling function is up to something called slowly varying function, is basically a power, right? And the exponent falls out and so on. So if you have something that scales like a polynomial, it must be a short range interaction and so on. And vice versa. If it doesn't, then it isn't. So that's if it swims like a duck and so on. Other things that are a little bit more intricate than pairwise interactions that we were quite happy that this theory could capture. Right. So there are these algorithms in meshing community, and this is the one that's a little bit like a textbook algorithm. In the sense that it's simple, right, and nobody actually uses it if they want to do industrial scale applications, but it's still good enough, so people still use it for research purposes. So basically the idea is you triangulate your configuration and then treat this Delaunay triangulation, by the way, and then you treat the edges of the Delaunay triangulation as if they were springs. Right, so there is a Hooke's law somewhere here. Without going into too much detail, so here is an anecdote about this interaction. So a person is Strang give this motivation. They say, well, this is like minimizing energy of a bunch of springs, right? So springs are pushing apart. You let the system evolve according to the Euler's algorithm. Therefore, you must be minimizing some energy. Well, it turns out that you're actually not minimizing anything, as a matter of fact. So there is this little technicality. You're actually maximizing a certain functional. And this is quite funny because what you're doing is not an energy at all. It's rather this concave interaction, which is good, which is beneficial in terms of maximization, obviously, and it leads to nice meshes. So I somehow get the feeling that I'm running out of time. So I'll tell you, by way of finishing, I'll tell you how things break up. Right? So you say, aha, surely something must not be captured by this theorem, and there is plenty of that. So there are these functionals. You can have a short range, I forget, was it P functional, right? Of this type, like Gerard told us earlier today, where you can have strong interaction and so on, but you will have two competing scales, right? So things will not quite work this nicely as I told you. Another way to make things break is to take S negative, very negative, right? And so if you push S far enough, instead of distributing, your points start clustering. So that's slightly similar to results that you can get for long-range minimizers. If you have some very degenerate kernels that are long-range, right? So if you have some really bad slope, very vanishing interaction functional for long-range interactions without any truncations or anything, you basically witness similar phenomena. So there are some things that make sense to investigate in this framework. Like I said, obviously there are things that you cannot quite, handle right away. There are some interesting non-isotropic situations where the interaction depends on the direction, but it's still strong and it still comes at a single scale, right? So it seems that, that should be possible to handle using these means. And then another interesting thing is, what about next order terms for these guys? Well, we're currently handling some kind of second order term for a simple kernel with fixed number of nearest neighbors, and that does involve a second order term. So that's a toy investigation that we're having. Okay, I suspect that I'm over time, but I couldn't hear what Mircea told me. So
you are.
so I have an alibi. Right. Thank you very much.
Thanks. Let's ask one last question. It doesn't seem like there is any question. But it was very nice. It would have been nicer to have you here, of course, and talk more about it. Yeah.
Okay, great.
Sorry.
Thank you for listening to